When work is done against a conservative force, like gravitational force, it gets stored as potential energy. Let's consider a body lifted vertically to a height h from the surface of the Earth. Some work needs to be done against the gravitational force of the Earth to lift the body, which is stored as potential energy in the body. When the body is released from height h, the body gains kinetic energy and loses an equal amount of potential energy. The law of conservation of energy holds good in this case, as the total energy of the system is constant. Like gravitational force, the electrostatic force between two charges at rest, expressed by Coulomb's law, is also a conservative force. The gravitational force between masses m1 and m2, separated by a distance d, is expressed as g into m1 m2 by d square, where g is the universal gravitational constant, which is equal to 6.67 into 10 raised to the power minus 11 Newton meter square per kilogram square. We can see that the gravitational force F is inversely proportional to the square of the distance d between the masses. Similarly, the Coulomb or the electrostatic force F between charges Q1 and Q2, separated by a distance d, is expressed as K into Q1 Q2 by d square, where K is a constant which is equal to 1 by 4 pi epsilon naught. We can say that the electrostatic force F is inversely proportional to the square of the distance d between the charges. When a force acting between two bodies is inversely proportional to the square of the distance between them, that force is said to be obeying the inverse square law. We observe that both gravitational force and electrostatic force obey the inverse square law. We know that work done against gravitational force is stored as gravitational potential energy for the mass in the gravitational field. Similarly, work done against electrostatic force is stored as electrostatic potential energy in a charged particle in an electric field. Let us now discuss the electrostatic potential energy of a charged particle in an electric field. Consider the electric field of a positive charge Q placed at the origin O. Let Q0 be a positive test charge located at point S. To bring the charge Q0 from point S to a point P closer to charge Q, some work has to be done against the force due to the electrostatic field Fe. The external force F required to move Q0 should be just about sufficient to overcome the electrostatic repulsive force Fe on Q0. Therefore, we can say that the magnitude of the external force F is equal to the magnitude of Fe. Let this be equation 1. The external force F should not give the charge Q0 any acceleration. The net force on Q0 must be 0. The charge Q0 must be brought from point S to point P at a very low constant speed. The work done to move Q0 from point S to point P is denoted by WSP and is stored as electrostatic potential energy for charge Q0. If we remove the external force F, then the charge Q0 moves away from Q in the direction of the electric field and gains kinetic energy such that the gain in kinetic energy is equal to the loss in its electrostatic potential energy. the sum of the kinetic and electrostatic potential energies of charge Q0 is always a constant or conserved. We know that the work done by the external force F to move charge Q0 from point S to P is denoted by WSP. This is equal to the integral of external force F dot dr in the limits S to P, where dr is the distance between the 2 points. Let this be equation 2. From equation 1, we know that the magnitude of the external force F is equal to the magnitude of force Fe due to the electric field. But the direction of the electrostatic force of Fe is opposite to that of the external force F. Therefore, we can say that external force F is equal to minus Fe. Let this be equation 3. Substituting the value of the external force F from equation 3 in equation 2, we get WSP is equal to minus integral Fe dot dr in the limits S to P. Let this be equation 4. In equation 4, the work done against the electrostatic force is stored as electrostatic potential energy. Hence, at every point in the electric field, the charge Q0 possesses electrostatic potential energy. Let the potential energy of the charge Q0 at points P and S be UP and US respectively. The work done by the external force F, as given by equation 4, is also equal to the difference in the electrostatic potential energies of the charge Q0 at the points P and S in the electric field. Let this be equation 5. The work done by the external force F is WSP is equal to delta U. Let this be equation 6. From equations 5 and 6, the work done by the external force WSP can be rewritten as delta U is equal to UP minus US. Let this be equation 7. The difference in electrostatic potential energy between 2 points in the electric field of any arbitrary charge distribution will be equal to the work done to move a charge from one point to another. The work done according to equation 7 is independent of the path followed to move Q0 from S to P without accelerating Q0, and is dependent only on the initial and final positions. Hence, the electrostatic force Fe is a conservative force, and the work done against the electrostatic force Fe is independent of the path followed. Adding a constant C to the electrostatic potential energy at points S and P will not alter the values of the difference in electrostatic potential energy between the charges and the work done WSP. Hence, we can choose a convenient reference point where the value of the potential energy is 0. Let point S be at an infinite distance from the charge Q. The electrostatic potential energy of Q0 at point S is US equal to U infinity is 0. Therefore, the work done according to equation 7 can be rewritten as WSP is equal to UP minus U infinity, which can be written as WSP is equal to UP since electrostatic potential energy at infinity is equal to 0. That is, U infinity is equal to 0. Let this be equation 8. Based on equation 8, the electrostatic potential energy of a charge Q0 can be defined as the work done by an external force to bring a charge Q0 from infinity to a point in the electric field of any charge distribution is equal to the electrostatic potential energy of the charge Q0 at that point. A parallel plate capacitor consists of two metal plates, each of area A and separated by a distance D. When the plates of the capacitor are connected to a battery, one of the plates is given an excess charge plus Q, and the other is given an excess charge minus Q. Due to this, a uniform electric field is created between the plates of the capacitors. Towards the edges of the plates, we observe fringing in the electric field. That is, the field is non-uniform when the plates of the capacitor are separated by some distance. We know that D is the distance between the plates. But if D square is very less compared to the value of the area A, the fringing effects can be neglected in the regions which are far off from the edges of the plates. Let the magnitude of the charge density be sigma for the plates with a charge Q on them. Then, sigma is equal to Q by A. Let this be equation 1. Let us assume the region on the left side of the capacitor as region 1, region between the plates as region 2, and the region to the right side of the capacitor as region 3. Let us now calculate the electric field in the regions 1, 2 and 3 with respect to the capacitor. We do this by applying the Gauss law to calculate the electric field in the regions 1, 2 and 3. We know that for a uniformly charged plane sheet of charge, the electric field strength E at some distance away from it is equal to sigma by 2 epsilon naught. Let this be equation 2. We use this result to calculate the net electric field strength in regions 1, 2 and 3. In region 1, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the left. We also see that due to the negative plate of the capacitor, the electric field strength E is also equal to sigma by 2 epsilon naught, and directed towards the negative plate and towards the right. Hence, in region 1, the net electric field strength E naught is equal to sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0, since the two electric fields are oppositely directed. Now let us look at the region 3. In the region 3, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the right. We see that due to the negative plate of the capacitor, the electric field strength E is also equal to sigma by 2 epsilon naught, and directed towards the negative plate and towards the left. Hence, in the region 3, the net electric field strength is equal to plus sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0. Since the two electric fields are oppositely directed in region 3 as well. Now let us look at region 2 between the plates of the capacitor. In region 2, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the right. we also see that due to the negative plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught. And directed towards the negative plate and towards the right. The region 2, which is in between the plates, has two electric fields of equal magnitude, sigma by 2 epsilon naught, which are both pointing towards the right. Hence, in the region 2, the net electric field strength E naught is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. On simplification, we get E naught is equal to sigma by epsilon naught. Let this be equation 3. Let the potential difference between the positive and the negative plates be equal to V. For a uniform electric field of strength E between the plates of the capacitor, we have V is equal to E naught D. Let this be equation 4. Substituting equation 3 in 4, we get V is equal to sigma D by epsilon naught. But we know that the charge density sigma is equal to Q by A. Therefore, we have V is equal to QD by A epsilon naught. Let this be equation 5. Now, capacitance of a parallel plate capacitor C is equal to Q by V. Let this be equation 6. Substituting equation 5 in 6 and simplifying, we get capacitance C is equal to epsilon naught A by D. Let this be equation 7. This expression for the capacitance shows that the capacitance is directly proportional to the area of the plates A. And inversely proportional to the distance between the plates. We know that the capacitance of a capacitor not only depends on the geometry of the plates, the distance between the plates, but also depends on the dielectric medium between the plates. When there is no medium between the plates, let the potential difference between the plates be V naught. The electric field strength be E naught, and let its capacitance be C naught. We know that the capacitance C naught is equal to Q by V naught. Let this be equation 8. The electric field strength E naught is equal to sigma by epsilon naught. Let this be equation 9. The capacitance C naught is equal to epsilon naught A by D. Let this be equation 10. After disconnecting the charging battery, let a dielectric medium fill the intervening space between the plates of the capacitor. The dielectric medium in between the plates will be now in the presence of the electric field in between the plates. We know that when a dielectric medium is in an external electric field, it is polarized. The net effect on the dielectric is that there is an induced positive charge density plus sigma dash on the right face and minus sigma dash on the left face. Due to this, there is a weak induced electric field, say E dash, in the direction opposite to that of E naught. Since the dielectric material has lesser number of free charge carriers as compared to the metal plates, which are conductors. Then, according to Gauss' law, the electric field strength E in the dielectric will be E is equal to sigma minus sigma dash by epsilon naught, which is less than the magnitude of E naught. The potential difference between the plates V is equal to ED, which now becomes V is equal to sigma minus sigma dash into D by epsilon naught, and hence V is less than V naught. In the case of linear dielectrics, sigma dash will be proportional to the external electric field strength E naught. But since E naught is equal to sigma by epsilon naught, it implies that the value of sigma minus sigma dash is proportional to the sigma value. Or we can say that sigma minus sigma dash is equal to sigma by K, where K is a constant of proportionality which is called the dielectric constant of the medium. Since the electric field strength E is less than E naught, and hence potential difference V is less than V naught, this clearly implies that the value of K must be greater than 1. For any dielectric medium other than air, K is greater than 1. Using sigma minus sigma dash equal to sigma by K in the expression for V, we get V is equal to sigma d by K epsilon naught. But since sigma is equal to Q by A, we have V is equal to Qd by AK epsilon naught. Therefore, the capacitance with a dielectric medium is C dash equal to Q by V. Here, it is of importance to note that since the charging battery is disconnected, the charge on the capacitor remains constant even after the introduction of the dielectric. Now substituting value of V in the expression for C dash and simplifying, we get C dash is equal to K epsilon naught A by D. Here, the value of K epsilon naught is called epsilon, where epsilon is called permittivity of the medium. For air, the dielectric constant K is equal to 1. Hence, we have epsilon equal to epsilon naught for air. For dielectrics other than air, we have the dielectric constant K greater than 1. The dielectric constant K of the medium is defined as the ratio of the permittivity of the medium epsilon to the permittivity of the free space epsilon naught. We know that C naught is equal to epsilon naught A by D. Hence, we can write C dash is equal to K C naught. Since K is greater than 1 for any medium other than air, we have C dash greater than C naught. We can also write K as the ratio of C dash to C naught. Thus, the dielectric constant K is a dimensionless quantity and has no unit since it is a ratio between similar quantities. Dielectric constant is also called as the relative permittivity of the medium and is also denoted by epsilon r. K is also known as the factor by which the capacitance increases when a dielectric medium fills the intervening space between the plates of the capacitor. Therefore, we see that by introducing a dielectric medium between the plates of the capacitance of the parallel plate capacitor increases. To obtain an expression for the energy stored in a capacitor, let us consider a parallel plate capacitor having metal plates X and Y, each of area A and separated by a distance D. When the plates X and Y of the capacitor are connected to a battery, one of the plates is given an excess charge plus Q and the other is given a charge minus Q. The plates X and Y are connected to the positive and the negative terminals of the battery, respectively. Let the capacitance of the capacitor be C, which is a constant. Let us now try to understand the mechanism involved in the process of charging of the capacitor plates from an energy point of view. In order to do that, we need to first imagine that the plates of the capacitor are completely uncharged. Now imagine removing infinitesimally small positive charge plus dq dash from the plate Y and transferring it to the other plate repeatedly. In this process, we see that the plate Y is getting negatively charged due to the buildup of excess negative charge on it, and hence the plate Y is at a lower potential. Simultaneously, we see that the plate X is getting positively charged due to the buildup of excess positive charge on it, and hence the plate X is at a higher potential. Therefore, the process involves transferring charge from the plate Y at the lower potential to the plate X at the higher potential. The electric field that builds up between the plates has a direction that tends to oppose further charge transfer. In other words, we can say that there exists a force that repels the transfer of charge plus dq dash repeatedly to plate X. Therefore, as charge accumulates on plate X, this repulsive force on the charges being transferred increases, and hence the amount of work done to transfer charge also increases. This work is actually done by the battery at the expense of its stored chemical energy. The work done to charge a capacitor is stored as electrostatic potential energy, U, in the capacitor. Now, let us consider a state of the capacitor where the charge on the plates of the capacitor is Q dash and the potential difference between the plates of the capacitor is V dash. Then, Q dash is equal to CV dash or V dash is equal to Q dash by C. Let this be equation 1. Now let us transfer the next additional charge plus dq dash to the plate X of the capacitor from the plate Y, and let the work done in the process be dW. From the definition of potential difference, we know that V is equal to dW by dQ. Therefore, dW equal to V dash dQ dash. Let this be equation 2. Substituting equation 1 in 2, we get dW is equal to Q dash by C into dQ dash. Let this be equation 3. Now, let us calculate the total work done W to charge the capacitor from 0 to a total charge plus Q. We know that W is equal to integral dW in the limits 0 to plus Q. Substituting the value of dW from equation 3 in the above expression and simplifying further, we get W is equal to Q square by 2C. This work done, W, is stored as electrostatic potential energy in the capacitor. Electrostatic potential energy of the capacitor is denoted by U. Hence, we get U is equal to Q square by 2C. Using Q equal to CV, we also see that energy stored U is equal to Q square by 2C is also equal to half CV square. Now, since Q is equal to CV, U is equal to half QV. A charged capacitor is analogous to a stretched spring. When the spring is stretched, it stores elastic potential energy, U, equal to half kx square, where k is the force constant of the spring and x is the elongation in the spring. When released, the spring loses the stored elastic potential energy. Similarly, the capacitor when charged stores electrostatic potential energy U equal to Q square by 2C. We see that the value of Q is analogous to the elongation x, and the value of 1 by C is analogous to the value of the force constant K. The energy supplied to the capacitor in the charging process is released when the capacitor discharges. We can also say that the energy stored in the capacitor is localized in the electric field between the plates. Now let us derive an expression to calculate the energy density of the region between the plates of the capacitor. The electric field strength E between the plates of the capacitor is equal to V by D, assuming a uniform electric field between the plates. Let this be equation 4. The electric field fills the region between the plates, and this region has a volume equal to area A into distance D. The energy density is defined as energy stored per unit volume. Therefore, energy density is equal to the energy stored by volume. This is equal to half CV square divided by AD, since the volume is equal to AD, which is equal to CV square by 2AD. Multiplying and dividing the right-hand side of this expression with D, we get energy density is equal to half CD into V square by AD square. Let this be equation 5. For a parallel plate capacitor, we know that the capacitance C is equal to epsilon naught A by D. Therefore, CD by A is equal to epsilon naught. Let this be equation 6. Substituting equations 6 and 4 in equation 5 and simplifying, we get energy density is equal to half epsilon naught into E square. This equation for energy density holds good for the electric field of any charge configuration in general.